Hello and welcome to another tutorial. We are going to continue our discussion on compiling Java applications using GraalVM native image. And so far we've looked at the fundamentals of Java applications, how we launch them using the Java runtime, which is a Java command. The prerequisite is that you have to compile your source files into the class files, because those are the binary files that the JVM or the Java tool understands. And then we said that eventually the goal is with the native image to transition from launching our Java application on top of a JVM, which is a virtual machine, to directly compile it to the native executable that runs by the operating system. And then we discussed a very important topic, which was command line arguments. And we said that there is a subtle difference between command line arguments for C++ binary applications when you write your application in C++ and the Java. And we said that the similarity is that both require a main method. In C++ or C, by convention, the return type of a main is int, but in C++ or in modern C++, you're not really required to return 0. But then in Java, it's void, because it doesn't make sense to basically return anything from main. And then we said that the main difference is the command line arguments that you pass to a C++ application, or a binary or executable binary that has been compiled, that had a C++ source and compiled to native binary, and Java. And we said that the main difference here is that Java, when you launch your application with the JVM or the Java command line tool, right? There are three types of arguments that you can pass. One is your application arguments, is this string array. The other one is system applications. Those are the parameters that you pass to the JVM using -d key equals value, right? And then the third one is just the global environment variables that are available for your terminal. Basically, you launch your Java application inside the terminal, right? Terminal is the application you use, is what you use to communicate with operating system. Now let's head back here. And previously we saw that we developed this application. It has hello world.class, has two dependencies, and inside our bash rc, basically we defined the class path and added all these to the class path, test2, test3, so that we don't need to specify the class path each time that we want to recompile the application. And we said that when you launch your application in the terminal, if this global environment variable called class path, and all caps, remember these global environment variables are all caps, if this is defined for your terminal, the Java compiler and the JVM or the Java command line tool both can pick it up and also add this to the list of directories that they can search into. And then we said that one point that I didn't directly mention is that when everything is available on your path or class path, then if you need to compile this hello world.java, which has a dependency on car and machine, then if you just run the javac command on this hello world.java, the Java compiler tries to basically compile all the dependencies first. So what I mean is that if I delete this car.class and this machine.class and then this hello world.class, right now I only have the source files. And let's make sure that we have access to this class path. Yes, it is. And now we are inside this test directory. Let's say javac and then hello world.java, and it's able to compile this because it also is aware of the class path environment variable. And not only it compiles the hello world.java, but before that it also searches for the dependencies, which are the car type and the machine type, and those are also available on the class path, right? Those source files are available, so that the Java compiler automatically compiles them first and then compiles the main Java class. So basically what I'm trying to say is that it's not actually, you don't need to go one by one and compile your Java files and then eventually get to the class that has the main method. You just make all those Java files available on the class path, and then once you run the Java compiler javac command on your on your main class, the class that has the main method, it automatically picks up or searches for the types, the dependencies of your particular class, and then compiles all the dependencies first, and then comes back and compiles the main class. So it's relatively easy. It's not that complicated, right? Obviously, you can go ahead and individually compile the car and machine, and that's what we did previously, but it's not necessary. The Java compiler has become very smart in terms of automatically picking up on all your dependencies and then compiling all the dependencies first. Now that we have this, we saw that we have three types of arguments. So string args, and then system properties, which is -d key equal value, and then you pass this application arguments after typing, writing the name of the main class. These -d key equal value are passed to the Java application or the JVM. So these are you type this before typing the name of the main class. And then there are global environment variables. These are the global environment variables that are available to the terminal at the time that you run your Java application. Now, if I say Java and then hello world, it's going to work fine because I don't need to specify the class path, because I've already specified the directories that my application needs inside this class path environment variable. And Java is aware of that, so it picks up on it. And note that, so let's do this one more time, and we're going to pass arg1, arg2, and then as you can see, basically it says that arg count is 2. Anything that you type after the name of the main class and there's a space there, then it counts as arguments to your Java application, part of this string array. And basically, but then anything that comes, but then you can also pass a system environment variable. So note that here in the source code, we're trying to find if a system property called name is set, and because right now we didn't set it, therefore it comes as null. But then we also check for an environment variable called LaTeX home, and if we find it, then we try to look at the version of this PDF LaTeX, which resides inside this LaTeX home directory, right? And we get the execute that command in terminal. We hook it up back to basically the JVM, and then JVM can print it back to terminal. So let's look at this. So Java -d name equals Bob, and then the name of the main class, hello world, and then arg1, arg2. And as you can see, now the name is system property is set. All right. Now, previously I mentioned that what happens, the question is what happens to these system properties when you compile your Java application to native binaries, right? Because when you compile your application, then you don't use the Java application anymore. You just directly launch it. And I've already done this. I've already compiled this application to a binary, native executable binary called hello world. Obviously, in the future lectures, we will see how to do it. But then right now I'm in this test directory. So if I say hello world, arg1, arg2, and as you see, it still works. It tells me that these command line arguments, we have two command line arguments. The first one is arg1, the second one is arg2, but this name comes out as null, right? And then it still searches for this global environment variable, LaTeX home. It finds it, and then it looks at the version of the PDF LaTeX. Everything works fine. So our Java application, now it's a native executable binary. We can directly launch this application. The question is what happens to those system argument -d key equal value. Now we can test it. If I say hello world and then pass a command line argument that starts with -d, name equals Bob. And as you can see now, this is very interesting that the way this native executable binary works, that it actually differentiates between the command line arguments that start with -d and the other ones that don't start with -d. As you can see, it still tells me that I have two command line arguments, or basically two arguments inside this string array, which are the arguments to my Java application. But the intermediate name was Bob, which means now this is passed as the system property. So even if you compile your Java application to native executable binary, it still recognizes system properties, and you can specify them directly as command line arguments when you launch this executable binary, but then it automatically differentiates between the system properties that start with -d and the others that don't start with -d, right? So it automatically understands this. So nothing gets messed up in your process of compiling your Java application into native executable binary. You can still set these system properties, and they will behave as system properties that you pass to your JVM, right? Now this is obviously different from C++ application. In C++, they don't understand this -d, so it just means you have 3 command line arguments. But here, because your native executable binary, inside of it has a compact version of JVM, so it can differentiate between -d parameters and then regular parameters that you pass your application. All right. Now, finally, we want to now start with default toolchains, and obviously, in order to compile a Java application to native binary, we have to have a compiler, and that's a platform compiler, or which is called a default toolchain. Every operating system comes with its own compiler. Vendors usually, so these compilers are either proprietary, which means people who develop the operating system provide these compilers, or this could be open source. For example, in case of an open source operating system like Linux, there are open source compilers that can compile applications for the Linux operating system. So let's start with macOS default toolchain. So platform toolchains are compilers that compile source code to binaries for CPU, and usually they're developed for C or C++ application. Obviously, older programming languages like Pascal, or those ones also have their own compilers. In general, there is no restriction on what kind of programming language you use, as long as there is a compiler for that programming language that can compile to native binaries for the CPU. So not only the operating system is important, but the architecture of the CPU is important, because different CPUs use different basically instruction sets, right? For example, ARM CPUs have a different architecture than x86 or x64 Intel or AMD CPUs. Therefore, the kind of instruction sets that they use is also different. For example, you might have heard that x64 CPUs like AMD and Intel, they use a CISC architecture, which is a complex instruction set, whereas ARM CPUs use a simplified version of the instruction sets called the RISC, or reduced instruction set, which means ARM instruction sets are much easier, but complex instruction sets in the Intel or AMD CPUs means with one instructions you can execute more complicated tasks, but it requires more complicated circuitry, so more power consumption. That's why ARM CPUs have basically much lower power consumption, for example, right? So right now we don't focus on the hardware for now. Let's just assume you typically have a CPU which is x64 architecture. If you have any other CPU like ARM, then you have to find a compiler that allows you to compile your source code to native binary. And every platform, every operating system has to provide some sort of default tool chain so that people can develop applications for that platform, for that operating system. The reason that different operating systems have different compilers, because the kernel that they use are different. Kernels are basically a very a group of files so let's say operating system, they all also developed with C or C++, and they provide an API for others, some functions, right, for the developers, so that the developers can use those functions to call some basically to perform some hardware operations, reading from the disk, for example. So for example, in C++, if you just use a file input stream or fstream or output file stream, something like that, those have calls to the kernel files, right? In Windows or macOS, the kernel API is different. Therefore, you cannot, when you compile your application on different operating systems, the binaries are different. That's why the binaries are not compatible. So macOS, you can just go ahead into App Store and install Xcode. It's a very big application. I think it's about 12 gigabyte or so. But in fact, for just trying to compile applications, you don't need to install the entire Xcode, because part of the Xcode is just a GUI that comes with it, and it provides a lot of tools for developing applications for different hardware like iPhone, iPad, etc. But we're just interested in getting the compiler that allows us to compile for macOS, right? So you can just use the toolchain that comes with the Xcode, and it's called command line tools, right? So either go ahead and install the Xcode app from App Store, or just open up a terminal and type xcode -select -install. So if we go, let's go back to the PowerPoint. Let's open up a new terminal. And if we just say xcode select -install, it gives me an error saying that the command line tools are already installed. So there is no update for it. If you want to update something, go to the software update to install updates. But right now, I've already installed the command line tools, and therefore there is basically no reason to install it. The first time, if you have not installed it, you can either use this command or just open up a terminal in macOS and type, for example, G++. If you haven't installed it, again, the terminal recognizes that you're trying to use the command line tools, a compiler, the platform compiler. So it opens up a prompt and asks you whether you want to install the command line tools. And you just say yes, it downloads some stuff. All right, so by default, this command line tools comes with Apple Clang compiler. And then when you install it, it actually creates aliases. So we know some people prefer G++ command on the terminal to compile their applications. Some people prefer C++ to compile their C++ application. Some people prefer GCC, to type GCC to basically compile their C applications, or Clang to basically compile their C applications. And you see all of these commands, when you install it, all of these commands become a symbolic reference to the same thing, to the same xcode.app, contents, developer, user, and then basically the same thing. So these are not different things. You're just using the Apple Clang. These are just aliases depending on what you want to do, right? So and G++, as you can see, it goes to library, developer, command line tools, SDKs, macOS, user, include, C++. So this is the directory that has all the header files for the C++ compiler that comes with Apple Clang, and this is a proprietary, so it's not open source. And then it's in the bin directory of the Xcode, right? Xcode app, contents, developer, toolchains, and then xc, toolchain, user bin. So if you run C++, it just points to the same directory, bin directory, and same header files, right? So the same thing. GCC, and then same thing, and then Clang, also same thing, points to the same directory. So all of these are the same, and these aliases get generated when you install your application. And if you want to check that your application is successfully installed, right? Command line tools are installed in applications, xcode.app, contents, developer, and there is inside the developer there is a toolchains, and then xcode default.xc toolchain. This is a directory. You can open it, right click, view the package contents, and then there is a bin directory there that you can check. So if you install it and you want to double check, you just type, for example, G++ -- version. And if it shows you that G++ is available, the directory is bin directory of the Xcode, everything is set up correctly. And previously, we also actually we wrote a C++ application which prints something to the command line and also picks up on the basically on the command line arguments. We also had a class, a user-defined type called car. We overloaded the output stream operator so that we can push it directly to the console. And this was equivalent to basically overriding the toString method in Java, right? We said that in C++, classes don't implicitly inherit from a master class or like object or something, so they by default they don't have any insertion operator or toString operator, so you have to overload them as global functions. And then we saw that basically let's go back here, let's go one level up. So one level up and then go into the example, and then we saw that if we say g++ example.cpp, and then we want to name the output file something else, so -o and then my app, and if this doesn't give us any error, it means the compiler is compiling fine. All the include header files like IO stream is available to us, and then we are able to, and then my app, and then we saw that you can pass command line arguments. Everything works fine. For a C++ application, it doesn't matter if your command line argument starts with -d, it just treats it as a regular arguments, right? Whereas we saw that for the Java application, this will get treated differently because there is underlying JVM that also accepts the system properties instead of command line properties. Alright, so this was the introduction to the macOS default toolchain. In the next lecture, I will show you the basically the Linux and Windows default toolchains. I'll show you how to install them, especially Windows. macOS and Linux are much easier to deal with in terms of developing applications because they either by default come with their compilers or it's very easy to install them. macOS is very easy. Linux usually comes by default with the compiler, especially if you install a popular distribution like Ubuntu, which is also my favorite. It definitely comes with the GCC, which is default toolchain for Linux. You can also, for example, install Clang on Linux because it's open source, but you cannot install, for example, Apple Clang for Linux because Apple Clang, first of all, it's not compatible. Second of all, it's not open source. So I hope you enjoyed this lecture. Please stay tuned and I'll see you in the next one.